Hi everyone. In this video, I'm going to show you how to perform the data analysis for the Joule-Thomson lab. And to begin, we're going to need some of the values that we got from the ambient situation, where we measured the pressure and temperature of the system, of the Joule-Thomson apparatus, before the gases were flowing. So assuming that you measured those quantities, I'm just going to make up a few of my own quantities and perform sample calculations so that you can see how to do it. We'll have a pressure in kilopascals, and I'm just making up a number, 99.63. You may have a different number of significant figures. That's fine. The calculations are exactly the same one way or another. And then we'll have a certain value for T1 in degrees Celsius. And again, just making up a number here, 21.24. Then we're going to have a T2 in degrees Celsius, and that's going to be a 21.67. So now those two temperatures were measured using different temperature probes, and in a perfect world, they should be the same number. However, the two probes that we were using are a slightly different design, made in different factories, perhaps at different times. So they're going to give you a different absolute temperature. But that's okay, because we don't care about getting an accurate absolute temperature. We mainly care about just getting accurate temperature changes. And so we're going to need to make a correction to this bias, because both of these temperatures have a certain bias. Who knows in what direction they are, but if we just account for the bias of one of them to set these two equal, then we're going to be able to analyze all of our data correctly. And so we need to calculate a correction to one of them, and I'm just arbitrarily choosing T2. And the correction is just going to be, what do I need to add to T2 in order to make it equal to T1 before these gases were flowing? And it turns out that I would need to add negative 0.43 to T2 in order to get T1. So from now on, whenever I get T2 values, I'm going to correct it by adding negative 0.43. Okay, now you see that I have prepared a table of my pressures and temperatures, and I'm doing this by hand, but I would highly recommend that you do this using Microsoft Excel or some other spreadsheet software to record all these different values. And obviously I'm going to have more pressures, more temperatures, and for two different gases. But I'm just going to show you on a few of these numbers so that you can kind of get the gist for what's going on here. So assuming that you've got all your data in this same format, now we're going to need to calculate a correction to the T2 values. And it's also going to be in degrees Celsius. And that's just by adding this correction term to each one of those T2s. So I get 20.74 for this one, 19.86 for this one, and 19.03 for that one right there. Okay, the next step is to calculate the delta T's, and since we're subtracting two Celsius values, we might as well just call it Kelvin, units of Kelvin, because subtracting two absolute Celsius values will give us a delta T in Kelvin. And then we've also got a delta P, and those are going to be in kilopascals. Okay, so our delta T values are going to be equal to T1 minus T2, and T2 corrected, that is. And that's backwards from what you might expect. Usually delta T is T final minus T initial, but in this lab, if we do that, we're going to get all negative values, and normally we'd just have to roll with it, but since we care about the slope of a regression plot that we're about to make only, we don't care about the actual quadrant that the data is in, it's going to be okay to flip the signs of both delta T and delta P. So our first delta T is 0.54. That's our T1 minus T2 corrected. Then 1.60 for that one, and 2.32 for that one. Okay, and then for our delta P, it's going to be equal to P1 minus P2. We've got our P1 right over here. That's our P1. So what's our P2? Our P2 is always going to be this value up here, because we're assuming that when we measure the pressure of the room before we had the gases flowing, then the pressure of the room is going to remain essentially constant. So we'll always just be able to subtract that one right there. So that's our P2 for everything. And so when I subtract each of our P1s by that one P2, these are the values I get. 106.88, 208.39, 315.26, so on and so forth for all these columns. And at that point, we've got a series of delta T's and delta P's. Okay, down here I've drawn a plot that you're going to be making using Microsoft Excel. And on this plot, the delta P's are on the x-axis and the delta T's are on the y-axis. Now watch out, because Excel might, by default, flip these axes, so you need to make sure that you've got the pressures on the x-axis and temperatures on the y-axis. And once you do that, you're going to plot all of your data points from your columns of delta P's and delta T's, and it might look something like this. Who knows? And we're going to create a trend line, and the trend line is going to need to go through the origin at 0, 0. And if you think about why the trend line has to go through 0, 0, recognize that if delta P equals 0, that means the pressure is equal on either side of the frit. So therefore, there should be no temperature change. So that's why we set it through the origin like that. And then once we create a trend line equation, we get a y equals mx plus b equation, but b of course equals 0 because we've set that intercept. And this slope value right here is the one we want. That m equals our Joule-Thomson coefficient. And the units are going to be in Kelvin per kilopascals. Unless you converted the pressure to a different units, like megapascals, in which case your Joule-Thomson coefficient would be in those units. So you're going to have to repeat this analysis for both gases. So say we've gotten to this stage and we want to compare to the Joule-Thomson coefficients in our textbooks, which are in Kelvin per megapascal. I'll show you just briefly how to convert a Joule-Thomson coefficient in units of Kelvin per kilopascal into megapascals. It's as simple as doing a dimensional analysis conversion, recognizing that there's 1,000 kilopascals for 1 megapascal. And that's going to equal our Joule-Thomson coefficient in Kelvin per megapascal. Okay, another requirement that I have for this lab is to calculate the uncertainty in the Joule-Thomson coefficient, or the standard error of the slope is another way to put that. And I would recommend using the linest command in Excel, Microsoft Excel. That's probably going to be the fastest and easiest way. However, in the protocol, I do outline how to get the standard error of a slope. And you can also refer back to your analytical chemistry textbook to see how to do that. But you're going to have to look up online how to use the linest command, because it's different for different versions of Excel and different computers. And it's not possible for me to really show it here on this video. So you should be able to figure it out if you look that up. But I would like to talk about what happens once you get that uncertainty or that standard error. Because say that you get a Joule-Thomson coefficient, and the Joule-Thomson coefficient itself equals 8.35 Kelvin per megapascal, and then the uncertainty of that, let's say it's 1.59. and uncertainties have the same units as their values. That's an important thing to remember. How is the right way to express that value in your lab report? You might say, oh, I would just do 8.35 plus or minus 1.59. Unfortunately, that is wrong. And the reason why it's wrong is because uncertainties have only one significant figure. So the right way to express this value would be 8 plus or minus 2, because we round this to one significant figure. Although it is also possible that if the uncertainty begins with the number 1, your other instructors might want you to keep 2 sig figs, and that's fine. I'm okay if you choose to keep 2 sig figs if the first digit of the uncertainty begins with 1. So in that case, you would write 8.4 plus or minus 1.6. Either one of those are okay. This is not okay. 8.35 plus or minus 2. And what's wrong with that is the uncertainty digit needs to end at the same digit as the value. So because these are less precise than the uncertainty, they're meaningless. So we need to keep it at 8 plus or minus 2. We would cut those off, truncate those. Lastly, I want to show you how to do uncertainties in scientific notation. Let's say that we had 8.9 times 10 to the negative third, and then we have an uncertainty of 7 times 10 to the negative 4. As you can see, that's quite ugly. There's a much nicer way to express this uncertainty. You would do 8.9 plus or minus 0.7 times 10 to the negative third. So we put the value and its uncertainty into the same scientific exponent, and that looks a lot nicer.